Good evening. I'm Karen Taylor, Program Director of the General Society of Mechanics and Tradesmen, and I'm very pleased to welcome you to the General Society and to tonight's lecture, which is part of the Labour, Literature and Landmark Lecture Series, and in fact is the final Labour lecture of the spring series. The Labour, Literature and Landmark Lectures are supported in part by public funds from the New York City Department of Cultural Affairs in partnership with the City Council. I would also like to thank the American Society of Civil Engineers, especially the Met Copri section, and Dominique forgive me, Dominic, I'm going to mangle your last name, Dominique de Arganzio, for their assistance and promotion with this event. For those of you who might be less familiar with the General Society, a brief introduction. The General Society of Mechanics and Tradesmen of the City of New York was founded in 1785, and we are now 232 years old. This, in fact, is our fifth home. Our educational and cultural programs include our tuition-free Mechanics Institute, the General Society Library, our upstairs Lock Museum, which, by the way, you're welcome to visit after the talk this evening, and our nearly 200-year-old lecture series, of which tonight's lecture is part of. You will find an informational postcard on your seat that provides background information on the Society, and anyone who's interested in library membership, you'll find some information on that on our registration table. Tonight's new lecture is about the new NY Bridge to replace the Tappan Zee Bridge. And I'm very pleased that we have the project manager for the delivery of the bridge here to talk about the project this evening. David Capobianco is the design compliance engineer and project manager for delivery of the NYS Thruways Authority New Y Bridge project. Mr. Capobianco managed the concurrent development of the environmental impact statement and the design build procurement, including the technical evaluation of proposals and the selection process. Prior to his involvement in the Tappan Zee Bridge replacement, he held positions as the Director of Structural Design and Highway Design for the Authority. It is my great pleasure to now introduce to you David Capobianco. Thank you.
Thank you very much, Karen. It's a pleasure to be here to speak at such an impressive facility and in front of such an impressive organization. And I commend you for your efforts in enhancing the development of educational opportunities for the trades. I think today it's more important than ever. So very happy to be here. So for tonight's presentation, I'll give a general project overview. I'll talk about the design build procurement, of course, the bridge itself with the approach spans and the main span. I'll talk about some of our environmental challenges, which we had many, some of the construction progress, and then finally end on the builders, the laborers and the people involved in constructing this huge piece of infrastructure. First, to set the mood, have a little video that, what's a big project without a time-lapse video, right? right, I hope you enjoyed that. All right, so now a little bit about the project. So the bridge was originally part of a 30-mile multimodal corridor project, which stretched all the way from the village of Suffern near the New Jersey state line to Portchester near the Connecticut line. Here you see the unusual alignment of the bridge. This is an aerial. The bridge is 3 miles long. It carries the thruway, which is Interstate 87 and 287 over the Hudson between the Nyack and Rockland County to the west and Tarrytown and Westchester County to the east. Now, the unusual alignment is due to a couple of considerations. One, we have the challenging geology of the Palisades, which are those rock-formed or glacially formed rock cliffs on the Rockland side. Nice to look at, but not so nice if you want to build a bridge. And then we also have here this light blue line, which is the jurisdictional boundary for the Port Authority of New York and New Jersey. So if the bridge is south of that line, someone from the Port Authority is up here today talking about this project and not me. The main span is a suspended cantilever truss, and there's 198 spans in all on the existing bridge. So the significance of the Tappan Zee, it's strategically located and meets the criteria for critical infrastructure according to the Department of Homeland Security. It's a primary gateway for goods being delivered to New England from the ports of New York and New Jersey. It's obviously in a major commuter corridor as well, and also receives a good deal of recreational travel on weekends, especially this time of year. So it's important to both the local, regional, and national economy. Why do we need to replace the bridge? Well, it was opened in 1955 and said to have a service life of 50 years. And that turned out to be a pretty good estimate, because it was in the late 90s and early 2000s when the Thruway Authority needed to spend increasing sums of money just to keep the bridge operational. The bridge carries 145,000 cars a day, which exceeds the design that was considered by a good amount, 40% for what it was planned for. We're always on the morning and afternoon traffic reports, which is never a good thing. The accident rate is twice the average for the whole thruway system. And that's exacerbated by the fact that we don't have any shoulders for emergency vehicles or any disabled vehicles. So even a minor fender bender, someone with a flat tire, there's nowhere to go and results in significant backups. There's no mass transit capability. Remember, I talked about the corridor study and the desire for mass transit at some point in this corridor. And also we have seismic and other structural deficiencies, but I can assure you that the bridge is safe, so don't worry. So in 2011, after a decade of study under the corridor project, Governor Cuomo decided it's time to build the bridge, and we pivoted from that 30-mile corridor project to a standalone bridge project. And he laid out several objectives at that time. One, build a safer, transit-capable bridge, and going back to the corridor study. Create jobs and economic growth. We were just coming out of the 2008 recession, so there was a desire to improve the economy. 100-year service life before major maintenance. We didn't want to come back in another 50 years and have to do this again, unlike the first bridge. Sensitive to the environment and the community, we wanted to go above and beyond the regulations and be good stewards of the environment. We also wanted to be good neighbors to the community. The communities on each side of the bridge were kind of under a cloud for a long period of time, not knowing if the bridge was going to be replaced, what the impacts would be to their communities, because when the bridge was originally built in the 1950s, it had a pretty significant impact on both the Rockland and Westchester side, as you can imagine. So we had a good neighbor policy for the project. And we wanted to deliver the project on time and on schedule, and that got us to the design-build project delivery mode. So here's an overview of the existing bridge. We have 7 lanes, no shoulders, as I mentioned. We have a central movable barrier, so twice a day that barrier is moved to allow a 4th lane in the peak direction 4 lanes eastbound in the morning, 4 lanes westbound in the afternoon. So I'll go through a little bit of the sequencing or the staging of construction. Here's the existing bridge, and the new bridge, or bridges, I should say, will be built immediately north of the existing. Sorry, my clicker's a little temperamental here. Maybe I'll do it the old way. Oops. So we took advantage of available right-of-way to the north of the bridge, and were able to build the entire northern span without impacting traffic on the existing bridge. We're also able to build about 80% of the southern span or eastbound structure as well at this point in time, and this is the stage where we're currently at right now. Later this year, hopefully in a couple of months, we're getting ready to move all traffic from the existing bridge onto the northern span, which will then allow us to proceed with demolition on the ends of the existing bridge so that we can then complete the southern span. And that'll happen about a year from now in 2018. And then, of course, the last stage is to demolish anything that's left of the existing bridge. So the configuration, when all is said and done, will look something like this. The northern span, which is 96 feet wide, that's where we're going to have all 8 lanes of traffic in a couple of months. So that width was determined by the need to maintain traffic. But in the final configuration, we'll have 4 standard 12-foot travel lanes, a standard shoulder, 10 feet on the right. We'll have an over-wide left shoulder, which will provide the ability for a dedicated bus lane, again, thinking of the multimodal desire here. And also, significantly, we'll have a 12-foot wide shared use path for pedestrian and bicycle use, which is something that's obviously not available now to the communities to cross this part of the river by bike or walking. The southern span, or eastbound structure, is 87 feet wide, and that width was driven by the desire for operational redundancy. So what do we mean by that? Well, if something should happen to one bridge or the other, we wanted the ability to maintain traffic on the other bridge. So we built it a little bit wider just in case. In the final configuration, we have the 4 standard 12-foot lanes, we have the right foot shoulder, and again, the over-wide left foot shoulder. We also left a corridor in the middle, minimum 36 feet wide, and that was for potential future transit use. And I'll illustrate that a little bit too. On the landings, very limited amount of work, just that what's necessary to stage the work for the bridge construction. The shared use path will extend, actually it will go all the way into interchange 10 area here, where it will connect to other similar facilities on the Rockland side. We also have a permanent maintenance dock here for the thruway's marine vessels to maintain the new bridge. On the Westchester side, it's a little more complicated. We still have the roadway reconstruction. We also have the shared use path connecting to Route 9, which is South Broadway in Tarrytown. But we also have a number of thruway facilities, namely the maintenance facility and the state police facility. Now, we gave the contractor the option to either rehabilitate these buildings or to replace them and use this area as a staging area. They chose to replace it, so they had to move all of our staff to a temporary location about 8 miles away on the Rockland side, and then they used this area for their bridge work. Now that we're getting close to completion, they've started reconstructing these facilities for us. Also importantly, this is where the existing toll plaza was. It was a conventional toll plaza with 10 toll booths. We also had higher speed Easy Pass at this facility. During the development of this project, the Thruway Authority was just contemplating going to all electronic toll collection, which I think a lot of facilities or toll facilities are doing here down in the metropolitan area. So we were kind of at a watershed moment where we needed to decide if we were going to go in that direction. And this project kind of pushed us into that. Because as you can imagine, if we were to have a conventional toll plaza here with highway speed Easy Pass, we actually were affecting the entire eastbound bridge back to the main span with having enough distance to taper out to get into the toll plaza. So by going to all electronic toll collection, we reduced the footprint on the land, but also, more significantly, on the bridge itself. Less bridge to build and less bridge to maintain. I'll talk a little bit now about the design-build procurement, and most significantly, how it overlapped the environmental impact statement. So at the top, you can see the normal process for design, bid, build. You do your environmental documentation, analyzing impacts, doing your evaluation of alternatives. Then you do your final design, and then you go to construction. Design, build, normally, the permitting is upfronted a little bit, but you wait for your environmental assessment to be done to pick a preferred alternative, and then you go through the design-build procurement. Well, on this project, we kind of did everything all at once, and that was in the desire to get to construction sooner. As you know, I think our governor doesn't have a lot of patience, right? So sooner the better. We were able to do this because we had only one build alternative. Otherwise, you're not able to do this. So the proposers were able to focus on just the replacement option for the bridge. So this was challenging because we were meeting with proposers confidentially during the procurement process, and meeting with the public in forums such as this during the environmental impact statement, and meeting with regulatory agencies to talk about environmental permitting. So we would be reacting to various things that we heard from each of those audiences and having to make sure that the corresponding documents were reconciled. In other words, did something that the proposer said confidentially, did that fit into the bounds of the environmental impact statement? And did we want to perhaps, allow that or not? Or something happened in a public forum and we changed our minds about something, we needed to relay that to the proposers. So it was a very dynamic stage of the project and very challenging. So the procurement was a one-year process. This was the first design-build contract in New York State. So in November of 2011, we got enabling legislation. We released the request for qualifications. We received interest from 5 design-build teams. We shortlisted them to 4, and then we finally received proposals from 3. So it was the largest contract in state history. I believe it still is. And we issued a notice to proceed in January of 2013. Now, some of the things that made the procurement successful, we had to pay the unsuccessful proposers. And this was, we had to do a lot of convincing to the state comptroller to say that we have to pay contractors to submit a proposal. Very unheard of. But this was necessary for a couple of reasons. One was to instill confidence in the industry, again, this being our first design-build contract. But the other, because proposers spent significant amounts of money to submit a bid, up to $6 to $7 million. So they needed at least some compensation to offset that risk. We also did what we call smart early work. One of the things about design build is that you transfer risk from the owner to the design builder because they're designing it and constructing it. But in order to limit risk, you want to provide them as much information because it's still wise to limit risk because risk equals cost and their contingency costs particularly. So we did a test pile program and soil borings across the riverbed because the foundation work was probably the riskiest and most challenging part of the project. It was up to 40% of the cost. So we wanted to give them the best information we could to limit their risk. So we invited them out onto the barges when piles were being driven. We gave them lots of data from this exercise as well. We also had these one-on-one meetings with them, which were confidential in nature. We had a series of 8 meetings, and this provided a communication and an ability for us to answer questions so that they could refine their bids. And the selection process was a 4-part process. It was partly pass-fail evaluation, financial ability, and other evaluations. The technical evaluation, which was the quality of their bid, their proposal. Price evaluation, of course, and price and technical was a 50-50 evaluation. And then we had the actual selection committee. The selection committee was made up of industry leaders and some community representatives. Prior to the selection committee seeing what the price was, they ranked the proposals based on their technical quality. So then they did this in the blind. They didn't know the proposer's name. We gave code names. So they would rank 1, 2, 3, the proposers according to their technical merits, and then they were provided the price. So it would be easy if the highest proposer, as far as quality, number 1, was also the low bid. Then it's a no-brainer, right? But that seldom happens. So then they have to do what's called a trade-off analysis. And in this case, Tappan Zee Constructors was declared the best value proposer, and their bid was $3.142 billion. We like to call it the pie bid. It's also about the length of the existing bridge as well, 3.1 miles. I don't know if that's just a coincidence or not, but I don't know. So Tappan Zee Constructors is a consortium of 4 large firms: Floor, Granite Construction, Trailer Brothers, and American Bridge, which incidentally, American Bridge was the contractor that built the existing Tappan Zee. And HDR is the lead design team. So after 4 years with design build, what do we think? Well, it's definitely reduced our risk as the owner, as the number and magnitude of orders on contracts or extras is significantly less as compared to design bid build. However, you cede a lot of control because you don't have prescriptive requirements. It's more performance-based. So preferences are very difficult to have the design builder adopt, and they kind of resist any types of changes. And it also limits the amount of meaningful public input, after you select a design build team. We're also naive with results to in regards to the design schedule. It was very aggressive. We figured a 5-year construction project, they're going to be designing just in time for each element to be constructed up till maybe year 4. Well, they wanted the design done in 18 months, and that was largely so the contractor could procure materials and limit their risk from price escalation. A lot of projects at this duration, we would normally have price escalation clauses. So for asphalt or gas or steel, so if the industry price went up, the contractor would be compensated. In this case, we didn't have those escalation costs, so the design builder wanted to procure materials and lock in prices. I'll talk a little bit about the approach spans. And when I mention approach spans, that's everything except for the main span, the cable stay portion. And on a lot of bridges, the approach span is not significant. But when we have a 3-mile long bridge, that's the majority of the bridge structure in this particular case. So here's a rendering of what it'll look like when it's done. It's a typical steel girder construction. However, the spans are much longer than the existing bridge, 350 feet long. So we only have 44 spans for the new bridge as opposed to the 198 on the existing. So a lot less infrastructure in the river. As far as Tappan Zee Constructors' approach, it was all about doing as much as they could off-site. And this was for several reasons. This kind of illustrates all the locations that contributed to fabricating various elements of the bridge. This was for efficiency purposes, to spread out the resources that were required and to deliver all the material that was necessary for both of these bridges. It was also to improve quality, doing work in a controlled environment, and also to improve safety. Anything that could be done off-site on land is a lot safer than doing it over water at height. And obviously cost savings too comes into play. So some of the things that they had prefabricated were the pile caps. I'll talk a little bit more about this in a minute. Those were done in North Carolina. We also had the pier caps, which is this structure here on top of the pier columns, they were fabricated in Virginia and barged up to the bridge site. And then probably most importantly, they had a steel assembly facility just south of Albany, and I'll talk about that too in a minute. The foundations, as I mentioned before, the area of greatest risk and uncertainty, and that's because of the challenging underlying soil conditions of this part of the Hudson. You have the first layer, which is an organic silty clay, or as those of us non-geotechnical engineers like to call muck. And what happens with this muck is that the first 70 feet or so of a pile is basically driven by self-weight. So the contractor was concerned about actually losing a pile, never mind having to hammer it in place, it just sunk. After that, getting through that, then you encounter a hard layer of glacial till. So you think you've hit rock, but it's the glacial till, so you got to get through that. And then if you're lucky enough, you reach bedrock. But that bedrock is also is a lot of sloped rock conditions, so it's very difficult for piles to grab into that. So there was a large concern about pile damage. Luckily, over 1,100 piles on this project, and only one so far has been damaged. So the piles are typically steel pipe piles, open, 1 inch thick, varying in diameter from 3 feet to 6 feet. So here are those pile caps that were made in North Carolina. This is down at the fabrication facility. You can see how extensive the reinforcing is. On the right, there's a section that's being ready to put on a barge to deliver to the project site. Once it gets to the project site, it's lifted onto these piles that were driven. On the bottom of this tub, as we like to call it, there are there are holes that are 1 foot larger than the diameter of those piles. So a 4-foot diameter pile would have a 5-foot hole. And it was pretty amazing, the accuracy of this when you think about it. We only had a couple of occasions where they needed to chisel out a little bit of the concrete to make the tub sit on the pile, but largely it was done to perfection. Now here's the pier cap. These were made, again, precast in Virginia. Originally, Tappan Zee Constructors was not going to precast the pier caps, but because of the success with the pile caps, they decided, hey, why not? So the columns were cast in place. You can see the reinforcing steel sticking up here from the columns, and then there were sleeves that were in the bottom of this pier cap. So again, the precision that's needed for all this to go together. Another big element of this contract was a floating batch plant. We had 3 of these. It would have been virtually impossible to do this any other way, to have concrete delivered conventionally by truck. It would have been over 20,000 trucks being necessary for all the concrete that's necessary for the bridge. So these were all certified by DOT as a typical plant facility would be. Here's that pre-assembly yard. This is just south of Albany, about 100 miles north of the bridge site. So there were 2 primary steel fabricators, one in Pennsylvania and one in Virginia. They fabricated steel girders 100 feet long, 12 feet high, delivered them to this site, and then it was an assembly line fashion to then splice the 100-foot long girders into lengths of up to 400 feet long, and they would also conjoin 2 or 3 at a time. Any utilities were also put on between these girders at this site, again reducing the amount of work that needed to be done at height over the bridge. Once they were fabricated up at that facility, they were then placed on a barge and floated down the Hudson. You don't get a real appreciation for the size of these things at a distance, but 12 feet high, so double me. And then the other significant element, a piece of equipment on the contract, was this huge crane, which some of you may have heard about, the I Lift New York super crane, otherwise known as the Left Coast Lifter. It was originally built for the San Francisco-Oakland Bay Bridge, and luckily they had the foresight to think, well, maybe it'll be used on the East Coast. So they made it to just fit through the Panama Canal. And I mean just. It wasn't a lot of clearance. So that was brought to the bridge site. They had to wait for a super low tide to get it under the existing bridge with the boom down, and literally only having 4 or 5 feet of clearance. So this piece of machinery is able to lift up those 400-foot long sections of steel, 12-foot high, and 2 or 3 at a time. Now, being so big, it's very clunky to move this big crane. The boom doesn't rotate like most cranes do, so you just set everything in that one position. So it's a series of cables and tugboats that kind of maneuver this thing to set the steel in place. So it's a pretty complicated operation. First time they did this, it took about a day, but then after the learning curve, they reduced that to about half that time. All right, doesn't want to advance here. I guess it wants to set that last piece of steel. Here we go. And that video is not working, sorry. This should be technical difficulties here. Try this way. Here we go. So it's a little video of what it looks like when these steel assemblies are floated down the Hudson River and then set into place with the left coast lifter. So this was the first steel section that was set in June of 2015. All right, you've seen that already. Sorry about this. All right, so after the steel comes the structural deck, and that was also prefabricated panels. You can see this panelized system. They were made in Pittsfield, Massachusetts, and also in upstate New York, and delivered to the bridge by barge, and then placed on the steel. That was followed by the cast-in-place closure pours, stitching those panels together. And then, of course, the final piece is the overlay, which is the riding surface. Another neat design element for the bridge were these seismic isolation bearings. So it's sitting on the top of a pedestal, right? This is the bottom of a steel girder, and this kind of illustrates how this bearing works under a seismic event. So it allows the bridge to move in a controlled way to limit damage and also failure of the bridge during a seismic event. Oops. It also resets itself after a seismic event. Normally, after any kind of a earthquake, you would need to go to bridges that were affected and reset the bearings. This is kind of self-resetting. All right, shared use path, I mentioned this earlier. One of the unique aspects of the project, we have amenities on each landing associated with the shared use path. We also have 6 what we call overlooks, and each one has a theme. This is one near the Rockland side, fish and chips. So they also have amenities with seating and canopies, and this is one of the funner elements of the contract, and something that, again, the communities are looking forward to. Onto the main span, cable stay bridge. The towers are 419 feet high, about 100 feet taller than the existing truss. They're splayed outward so that there's no cabling or other structural element above the roadway. And that's important because there's no concern with icicles forming during the winter and falling on traffic. It also allows the Thruway Authority to do maintenance and replacement of cables without impacting traffic. Here's another view looking at the westbound bridge. Here's the shared use path, and then the overwide left shoulder, right shoulder, and again, nothing over the roadway, kind of nice open feel to it. The foundations for the main span, Piles are driven 250 feet to rock. And then within those piles on the main span, actually for all the piles, we have this, what we call a concrete plug, which is reinforced concrete that goes into the pile, in this case 140 feet or so, and that provides connection between the pile and the substructure. This illustrates the enormity of the foundation for the main span. It literally fits the same length as a football field. It's 64 feet wide, 14 feet deep. These are what are known as climbing forms or jump forms, and this greatly facilitated the construction of the towers. The towers change in dimensions as you get higher and higher, so these forms were able to be modified to adapt to the different changes in geometry as you went up the towers. And this kind of illustrates how that worked. So it was a two-frame system. You would jump the outside frame first, put reinforcing steel into the tower walls, then jump the inside frame, pour concrete, and continue. This was done in roughly 15 to 20 foot lifts, as we call them, and it took about 10 days to go through this sequence. Yeah. And once again, sticking here. All right, so the cable stays, there's 96 cable stays on each bridge. They vary in length and diameter and are all protected by a high-density polyethylene pipe. Sorry about this. This is what's happening. Oops, got to go back. All right, so I mentioned before that this was part of a corridor study. So the desire to have the ability to provide for future transit was part of this project. So part of the requirements was to design the foundations for the heaviest transit load, which is a E60 commuter rail. So if trains were added in the future, we wouldn't have to go back into the river. The foundations are capable of supporting commuter rail. What would be necessary, though, would be to modify the superstructure here for the main span, kind of take advantage of these inclined tower legs. We would conjoin the middle section of these legs, drop cables from that point, and then add a new crossbeam here that would enable one track in each direction. So it was a pretty elegant solution. They had to design this conceptually to show us that it was possible, and we had Metro North peer review it to make sure that they were on the up and up. For the approach spans, not as elegant a solution, but again, the foundations would not need to be modified, and this is just one particular way that you would be able to provide for future transit loading. All right, now to some environmental challenges, and we had many. The existing Tappan Zee Bridge is considered historic, and that's mainly for its foundation design and the buoyant caissons. There's also a shipwreck, believe it or not, nearby in a coal barge. Water quality was a big part of what we do. We've literally taken thousands of water samples at various construction stages. The new bridge is right in the path of oyster habitat within the Hudson River. We have endangered species, most significantly the Atlantic and the short-nosed sturgeon. And then we also have people, so we needed to deal with that as well. So one of the first things that was necessary for the project was to dredge. Now, once you get out of the navigation channel, which is 40 feet deep, this part of the Hudson River is relatively shallow, anywhere from 4 to 8 feet, depending upon the tide. So in order to allow these big pieces of equipment to function, they needed to do some dredging. Well, the environmental impact statement estimated that we would need to dredge 2 million cubic yards. Tappan Zee constructors reduce that, cut it in half actually, because they were able to design it more efficiently for what they planned to do. So it's kind of an example of how design build also reduced environmental impact. So here's some of the mitigation that we needed for the fish and underwater noise attenuation. So what was involved here is that we have these compressed air rings here that were lowered onto the piles, and they kind of created this jacuzzi effect here that you see on the right when piles were being driven. So you'd have this column of bubbles, we call them bubble curtains, that would be underwater that dampened the sound underwater that would ordinarily affect fish in perhaps a fatal way. So that was one thing that we did. For above water noise for the people, we had these shrouds that went over the top of the pile cap that kind of deadened the noise for the residents. Sturgeon monitoring, we had to do a lot of mitigation for the sturgeon, and this illustrates we have near and far field monitoring. So a lot of sturgeon have already been tagged, so we have monitoring devices that pick up those tags. We also needed to capture and tag about 100 sturgeon ourselves as part of the mitigation for the project. So scientists will use this to study the behavior of sturgeon during different phases of construction, how they reacted to noise, et cetera. And the sturgeon are pretty big fish. This is they're anywhere from 8 to 12 feet long, which is pretty amazing when you think about it for this part of the Hudson River. The oysters. As I mentioned, we affected an oyster colony, so we needed to harvest a number of shells and then move them to an area that was not impacted by the project to rehabilitate about 11 acres of oyster community. And then, of course, we have our peregrine falcons. We have a nesting box on the existing bridge. So the falcons are in residence from about February to about this time of year, when they have their chicks. So we had 2 this year. We have a naming contest with the schools in the area, and they get to name the chicks. So we have a new nest on one of the towers of the new bridge. So we're hoping that next year the falcons find their way to their new home. All right, I'll talk a little bit about the progress to date. Here you can see how construction progresses across the river, going towards the main span. This is a little bit further back from the main span. You can see some piles here just sticking out of the water, then pile caps rising out of the water, and then columns and pier caps, and then finally you get some steel at the very end. This kind of illustrates how we can only build so much of the southern or eastbound structure before we start impacting the existing bridge, which is here. This is the northern span we're able to build completely without impacting traffic. Here we have the left coast lifter in action, setting one of the last steel members for the approach span on the Rockland side. And on the main span, these steel sections are called field sections. So the main span is a balanced cantilevered construction. It's kind of do one side of the tower with the steel, then you put steel on the other side, and it's balanced in that way. After setting a section of steel, you would then install cable from that steel section up into the tower into what's known as an anchor box here. So you can kind of see the development, and this is done back and forth. Further along, here's the installation of one of these stay cables. You can see here, you know, their length, it's kind of like a wet noodle, so it requires several cranes to install these things. And then this is the last section of the westbound or northern bridge that was set in March of this year. And luckily everything lined up. We didn't have that cartoon where, you know, we missed. So that was a big day. And here, the eastbound is still under construction, and we're hoping to close that bridge September of this year or so. I'll talk a little bit about some of the workers, and there are many of them. Over 6,000 people have worked on the bridge over the span of 4 years. At the height of construction, there was about 1,100 to 1,200 on site at any given day. Right now, we're probably in the 800 range. Dozens of trades involved, not just heavy highway and bridge construction, but we have a number of buildings so we have vertical construction. We also have a lot of systems with communications and power networks, et cetera, as well as fire suppression system on the new bridge. And then we also have the behind-the-scenes folks, or those that don't wear hard hats every day, and that's people like me in the design and oversight of the bridge. And during the height of design, there were over 700 people at one point just working on the design of this bridge. Hopefully I have a little video here interviewing some of the workers.
My name is Christopher Tobacco. I work for TZC in Local 1556.
Brian Jones, my parent company is Trailer Brothers Construction. I'm the area superintendent for Pier 32.
I'm Lorraine Hart, a union carpenter, Local 279, working at the Tappan Zee Bridge. There's a lot of work involved, a lot of things you have to be careful of, a lot of safety involved, and it's great. It's a great experience.
I've hit a couple of big jobs like this, but nothing this size, so it's kind of interesting to see an entire bridge built up from the bottom.
It's a lot of work, a lot of challenge. I mean, the challenge of being away from home. You're working on some things that have never been done before.
Yeah, it's been very interesting. Last week was a year that I'm working on the job. It's a lot of juggling of getting everything going. So now it seems to be running pretty smoothly.
I've been a construction worker for over 30 years, and the projects I've worked on, some were substantial, but nothing compares to this one here. This is like a once-in-a-lifetime job, I think, for most people.
It's a good feeling, knowing that we're going to be a part of history. It's an American-made bridge, made by American people, local people. That's why I'm here.
It's mostly on the job training, so I didn't go to a specific school, but like I said, I came into this union as a diver, and that was transferable skills. So basically, they just took all my work skills, and I just expanded upon it, took classes after I got into the union.
I started out as an apprentice, like every carpenter has to start out as. I went to school for 4 years through the apprenticeship, also on-the-job training.
I spent 20 years in the carpenters union, came up through the unions, through the trades. Anybody who would like to get into this business, I mean, you have to like working with your hands, you have to like being outside. Someone who wants to be in offices, this is not their kind of work.
Well, you got to stick with it. I mean, once you get it in your head you're going to do it, you got to stick with it. It takes 3 years or almost 4 years to even take the license to get into one of these. So you got to be committed.
If you like being outside, you enjoy outside work, you love building stuff, come do it. It's awesome.
It's going to feel amazing to know that I had my hand in this bridge, and this is a massive project, and I'm so proud to be here and to be on it and to be able to drive across it with my kids and my grandchildren and say I helped build that bridge. I mean, it's just an awesome satisfaction. I get like goosebumps thinking about it right now.
I always tell people I don't build buildings or anything, I build landmarks. So, I mean, when you build a bridge, you're building a landmark, and that's something I always think about.
Yes, it is. All right. This a project of this size really makes you feel very small when you're on site. This person here, early on, he's working in the main span foundation. This is the foundation that's over a football field long, 64 feet wide, and 14 feet deep. So you really get a sense of the size of things when you put it in a scale such as this. Here we have some iron workers that are splicing some of the steel work together on site. And, again, did as much as possible off-site, but it obviously couldn't, we needed still to do some splicing of bolts on-site as well. Here are those jump forms or climbing forms that I showed earlier. They were called condos by the workforce, and I wasn't really quite sure why they were called that until I went up there one day, and they have all the conveniences of home in those condos. Again, it's a two-frame system, so they have a microwave, a refrigerator, and porta-john. They don't leave that site. Once they get to work, that's their home for 8 or 10 or 12 hours, whatever their shift is. And that's for a couple of reasons. I mean, access is by boat at this point in time, so it takes time just to get to where you're working. And then once you get there, you have to climb up these staircases to get there. And the more work progresses, the higher you're climbing every day. So these guys must have been in shape at the end of the project. Similarly, for the tower crane operator, even more so, here you can see where he lives, basically, for his entire work shift, because for him to get to work, he's climbing up this vertical ladder system in this red cage there. So again, you don't want to do that too often if you don't have to. Here's the inside of the big crane, the left coast lifter. It kind of looks like air traffic control system. Takes 2 people to operate it. They had to undergo 6 months of training before they lifted their first piece of steel. Working on the bridge, it's a different environment on the bridge. And this, once you're out on the river, as many of you may know, changing conditions, the climate, the temperature varies significantly from land to when you're on the bridge site. So it's usually very hot or very cold, very windy. There's seldom a day where it's just nice. So these guys are smart and they're protecting themselves from the sun with a little tent system as they work on one of the expansion joints here. This crew is installing the stitching for the deck panels that is part of the structural deck. And it takes a lot of people that aren't building to service those that are. And one of the more important things is making sure everyone has cold water, especially this time of year, but even in the winter. So it's amazing when you see barges that are literally loaded with hundreds of these water coolers or hundreds of porta-johns that need to be swapped out every day or whenever they're changed. This is the celebration of Safety Week that we had this year. Kind of gives you an idea of the number of people on the project. We had a nice opening ceremony on the main span. So some of the observations of people that work on projects like this. A lot of the engineering folks are big project people. They move with the work. It's almost like they're in the Army, and every 3 or 4 years they move from project to project. There are, a couple of locals, and similarly for the work crews themselves, it's a mix of out-of-town folks with local support. The logistics for this for projects like this is unbelievable. At one point, we had over 100 barges in the river and 40 cranes. So Tappan Zee constructors had a whiteboard in one of their conference rooms that kind of looked like battleships. They had all the marine equipment laid out and where it needs to go on any particular day. So just trying to figure all that out is amazing in itself. And it takes a world to build a bridge like this. I mean, literally. You saw all the places across the United States that fabricated elements, but we also had contributors from other countries. The main span designer is based in Vancouver. We had testing and fabrication of other elements in various other countries as well. And projects like this are all consuming, so it's you have to be totally committed, and it's kind of your life until it's done. So with that, I'll entertain questions.
Just so everybody knows, we are recording this, so please wait until the microphone comes to you before speaking.
My question is, in retrospect, what, if anything, would you have done differently, given the last 4 years' experience?
Wow, that is a tough question. Well, we weren't very educated as far as the design-build process. It's different than managing other contracts. So it's hard to say. I guess maybe we would have provided less direction to the contractor, because as soon as we provide direction, that risk balance shifts. Now we own it; they don't own it. So that's one thing maybe that we do different. And I don't know. It's hard to say what else. That's a tough question.
Do you have a rust issue? And you have to paint and repaint and paint?
Do we have a rust issue? Not yet. So the bridge, the girders are weathering steel, and then they're painted with either a 3 or a 4 coat paint system. So it's the durability should be about 20 to 25 years before we have to do any major repainting. But even then, if we do get some deterioration of the paint, we have that weathering steel underneath. So that kind of forms a patina that kind of eliminates rusting. So we're hoping that works.
How are you doing so far in terms of being on time and on budget?
That's another good question. So I'll take on budget first. Very well. We've had 4 what we call orders on contract, and you saw the original bid was $3.142 billion. We're still in the 3.1 range, so we haven't even crossed that 3.2 threshold yet. So budget-wise, we're doing very well. Time-wise, also very well. We're focusing on the end game, which is completing the project in 2018, and we're on track to do that.
During the 100-year life of the bridge, what do you expect to wear out first, and what quality controls do you have to do in all these different parts and materials in order to be fairly sure that you're getting what you hope for?
All right. Well, I was kind of anticipating a question like this. So one of the key elements for service life was that the design builder had to submit a corrosion protection plan to us, and that was to illustrate to us how they would meet that requirement. So what they did was, for each element of concrete, they had a specific mix design based on the environmental zone, or the exposure zone for each of these elements. So for instance, where we expect spray from de-icing salts, that was the most corrosive zone. So they would make sure that that concrete could stand up to that type of corrosion, and they did laboratory testing to ensure that. And they did this for steel elements as well, developing corrosion rates. For instance, for the piles, they estimated that the piles would lose about, I think it's 3/16 of an inch after 100 years. And then you still have the concrete inside the piles, which is reinforced. So that gives you more service life. So that was a big part of the contract, and a requirement that we looked at very seriously. Of course, you can never be certain. You're working with models that predict corrosion and durability, and a model is a model. So, but it's the best we have.
Two questions. Question number one, what concerns, if any, are there that your design and bridge won't function the way you want it to? That's number one. And number two, what energy production will you be making for the bridge, such as the cogeneration system?
Well, the first question, I think we're pretty confident that the bridge will behave as designed. The design builder had a robust quality control, quality assurance program. The Thruway Authority provided additional oversight. So I think we feel pretty confident in that regard. As far as the power, I don't have that information, so I can't really answer that question.
So you don't know if the bridge is producing its own energy to take care of.
I'm sorry. Yeah, we're not producing our own energy. We're relying on the grid system.
No cogeneration.
Correct.
System.
No.
Thank you.
Follow up. If you're relying on the grid, the electric, what happens with the pivot? If there's no electric?
We do have generators on each landing, so we are able to provide emergency power for our roadway lighting, for instance, and any other power that's deemed essential.
What is going to happen to the existing bridge? I think you said it was going to be demolished. At what point it was being considered for being converted to a recreational facility?
Yes, good question. There was a lot of desire to save the existing bridge, similar to walkway over the Hudson in Poughkeepsie, but part of the existing bridge is in conflict with one of the spans of the new bridge, so we needed to demolish at least part of it. And then there was also the concern with ongoing maintenance costs. Even though it would only be for pedestrians and bicyclists, you still are opening it to the public, so you're still responsible for a level of operations, and it's just, this is another financial commitment that the authority wasn't willing to undertake.
When you're demoing the old bridge, how deep down are you going to go to where they cut it off?
Good question. We're going 2 feet below what we call the mud line of the river bottom. So that will keep it out of the harm's way as far as any vessels, but anything below that can remain in place.
You have any suggestions for the name for the bridge?
That's been a lot in the paper recently. I think everyone has a suggestion. No, I do not.
Will any of the specifications for this bridge be taken and applied to later construction statewide through the Thruway Authority?
Yeah, as a matter of fact, not just the Thruway Authority, but other agencies within and even in other states, they've used our specifications and adopted them for uses on other projects. So, absolutely.
I was wondering, since you're opening that to pedestrians, how windy do you expect it to be out in the middle of the bridge?
Yeah, there's a big concern with, as I mentioned, the environment on the bridge is usually very different than it is on the land. So, it's going to be part of the challenge with the shared use path is to make sure that people are prepared for windy conditions. It's not unusual to get gusts of 20, 30 miles per hour or more. Certainly on windy days, you would think that we would have less people that would maybe walk on the facility. We've even talked about, at what wind speed would we say, no, you can't use the facility. So we're still kind of asking those questions and developing some protocols for that.
I have a real novice question, which is, could you repeat this further south so we could have something in addition to like the Lincoln Tunnel or instead of another tunnel?
Another tunnel, yeah. I wish we could. I know there's a lot of need for river crossings, and you can never have enough of them, right? Yeah.
With this kind of complexity and number of men, how was your safety record throughout the to date?
The safety record has been remarkable, really. We haven't had any fatalities, which is certainly good. For the existing bridge, I believe we lost 3 or 4 people. And when you compare our safety rate to other projects of this size, we're just below what's the average. So safety is a big concern. We take it very seriously, both the Thruway Authority as well as Tappan Zee constructors, and so far, so good.
My question was similar. On OSHA, were the OSHA individuals there on for safety issues?
Well, OSHA isn't typically on site. They come to. It's usually not a good thing when we see OSHA. It's usually they react to an occurrence, and we've had some instances where they were on site to do some investigations, but otherwise they leave it to the safety officials on the project.
Yes, on the pilings, can you go back to that slide easily? Is that possible?
I could try.
Because it looked like some of the pilings were floating. It didn't seem like the bedrock was even close.
Oh, that's a great observation, and I did not mention that. Yeah, so for a third of the river crossing, oops, lost it there. We can't reach bedrock. In this area here, bedrock is over 700 feet deep. So we had to use what are known as friction piles there, which were driven to about a depth of 340 feet. So it's basically sticking the umbrella in the sand deep enough so that you get the support that you need. Yeah.
From the pictures you had so far, I haven't seen too much fendering in case of a barge or vessel impact.
Yeah, that's a really good observation too. Let me see. So here you can see on this pile cap, this black covering here. So that's a fendering system that's built into the pile cap. We don't have a separate external system as the existing bridge does. So it's kind of integral to the pile cap. Oh.
David, thank you. That was absolutely terrific. And it was completely, was a riveting presentation. I couldn't even believe you'd finished, actually, because I was thinking, it was absolutely engrossing. And I really appreciate that for many of us in the audience who are non-engineers, that you presented a complex subject with such clarity. It was absolutely fascinating. And honestly, I was just thinking about, because we talked about the landmark, and this will be a landmark, and it's very rare that we're at the start of a landmark, and it's just extraordinary to think that this is going to be here for another 100 years, and very few of us probably will be here to see the end of the bridge. But I want to thank you on behalf of the General Society. Thank you so much for such a fantastic presentation, David. Thank you. And David, on occasions like this, we like to thank our speaker by making a presentation. And so we have a citation, and to present it is Victoria Dengel, our Executive Director.
Thank you. And David, yes, thank you. That was wonderful. And as we say with so many of our lectures, thank you for making us look at something in a way we've never seen it before. And I don't think there's a person in the audience that won't drive across a bridge and think more about the structure. So thank you. And I also want to thank you as my beloved father, who was also the 1982 president of this organization of the General Society of Mechanics and Tradesmen. was a Local 14 operating engineer. So I'm always so happy when I see cranes. I can't get enough of them. So thank you. Those were very happy sights. So on behalf of the General Society of Mechanics and Tradesmen of the City of New York, founded 1785, we express our gratitude to David or Capobianco, project manager delivery, building a new New York state-of-the-art bridge to replace the Tappan Zee Bridge, for his participation in the General Society of Mechanics and Tradesmen Labor, Literature, and Landmark Lecture Series. So thank you. Okay, thank you. Thank you. And we have some happy news for David, who expressed delight at his first visit here at the General Society of Mechanics and Tradesmen. So we'd like to see you again. So we have made you a lifetime member of the library. And then your poster.
Oh,
so.
excellent. Wow.
All right.
I'm very humbled. Thank you
Thank
very
you.
much.
Thank
And
you.
excellent questions.
Thank you.
Thank you.